Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're happy to have Bobby Kleinberg here, visiting for a couple of days, unfortunately not longer. We should try to get him to visit for longer at some point. And he's going to talk about some very nice new work. Well, I guess 2 pieces of work you said, or is it, well, yeah. Okay. Converting any algorithm into an incentive-compatible mechanism.
All right. Thanks for the introduction, Jennifer, and to Madhu for inviting me, and to all of you for coming. In the spirit of the holiday that's beginning at sundown today, I want to publicly announce that I'm granting amnesty to anybody who has to leave the room in the middle of the talk. I won't take it as a referendum on what you think of the talk. A corollary of that is that if you do really hate the talk,
the amnesty is Yom Kippur, no?
It's good to be merciful all year round. A corollary of that is that if you are leaving because you really hate the talk, you have to do something emphatic, like go pshaw as you get up out of your seat, because otherwise I'll have no way of knowing that that's why you left. To introduce, that's a good point, actually. This presentation is a unified presentation on 2 papers that are joined by the theme of randomized reductions in mechanism design. And so to introduce that theme, I like to start with a hypothetical tale about a Netflix competitor that has just been founded called FlexFlix. It resembles Netflix in that people go online and make a queue of movies they want to watch, and then the movies get sent to their home. It differs from Netflix in that the queuing policy is more flexible. In addition to saying what movie you want to see, you can also list a priority level that they may optionally use in deciding to re-rank the elements of your queue. So for example, this user named Petra is evidently into 21st century German art cinema, but she's not above watching the occasional cheesy action movie now and then, but she assigns it a low priority. On the other hand, another hypothetical user, Bobby, is basically just interested in watching the biggest summer blockbusters. But doesn't mind seeing a foreign film once in a while, especially if it's the one that just won the Best Picture Oscar.
There is the one type of ordering. If so, why would you ever put a high beneath a medium?
In your own Netflix queue, do you always have the movies sorted by the ones you most want to see come earliest and the ones you least want to see come latest? I personally don't, because then after the first month or so of belonging to Netflix, life would become pretty boring, and I wouldn't look forward to getting new movies. Actually, now that I have a baby, it's not the first month or so, it's the first decade or so of belonging to Netflix is how long it would take me to get through the top of my queue. Okay, but nevertheless, I do think it is realistic that users of a movie queuing service would not just put all their high priority movies at the top.
So this picture of you was long before you.
True, but off topic. So the reason these priority levels are helpful is that at some point in the future, maybe Petra has watched her first 2 movies, as has Bobby. The next 2 movies that are set to go out are Avatar to Petra and The Secret in Their Eyes to Bobby. And FlexFlix, which only has 1 copy of Avatar, realizes that there's a risk right now that they might send it to Petra, who hangs on to it for a long time, and then Bobby doesn't get to see Avatar when he wants. This is no longer a problem because I just saw Avatar for the first time in my hotel room last night. And I have to say it is as formulaic as it was. So what FlexFlix would do in a situation like this, it would swap the first two movies on our respective queues. Bobby would get to see Avatar right away, Petra later, and in exchange, the designers of FlexFlix were not idiots, so they realized that there's a potential exploit where a user could just claim that every movie is high priority for them, and then they'll continually get the stuff they want immediately while other people pay the price of getting their stuff ranked lower. So what they do is every time a swap like this takes place, they make a little micropayment to the users who were willing to give up their highest up on their queue pick. In this way, they hope to keep the users of the system honest.
Sorry, so what's the objective? Why does the system, does it want to give high priority things to people first?
Social welfare or whatever?
Since the talk will not be about movie scheduling, I elect not to answer that question. And if you think that this is a lousy business model, then you can consider my answer to be confirmation that I also think this is a lousy business model. But actually, stepping off topic, I think this is a reasonable model of a service that users might like to subscribe to. I couldn't assign a numerical value to their utilities, but I don't just put all my highest priority movies at the top of my queue. However, it is the case that if I was, on a day when the very next movie that was due to be sent to me was one of my low priority ones, if Netflix suddenly announced to me, guess what, Bobby, we took that movie from the top of your queue and moved it down to number 5, I wouldn't be too upset about that. So like I said, I can't assign numerical values, but I am not going to completely back away from my contention that this is a service that reflects actual utilities of users. There's no limitation, but if you list movies as low priority, you're more likely to get these micropayments. Yeah. Yeah.
Can every user observe the total inventory and every other person's queue? In your theoretical model?
No. You can only see your own queue. But a blanket statement about all these questions is this is just a motivating example to illustrate the notion of reductions in mechanism design. And movie queues, starting 2 slides from now, movies and queues will not appear in the rest of the talk. I should start using a different name in my talk. Okay. It's easy to see how this system could backfire. If the micropayment system is not well designed, then users could start trying to cheat the system in ways that do not benefit society as a whole. Petra might decide, for example, that she's going to load up her queue with low priority action movies because she predicts that none of them will actually ever get sent to her. They'll just keep getting swapped down and she'll pick up a little change every time that happens. But not being an expert on action movies, she doesn't know that Speed Racer sucked and nobody wants to see it. And so, to the detriment of the overall system welfare, this one ends up getting sent to her and she collects no payment. So what happened here was that FlexFlix, which may have been quite sophisticated in the design of queuing and scheduling algorithms, was not sophisticated in the design of incentive mechanisms. And as users learned to manipulate the system, the quality of their queuing and scheduling, which is what they really care about for their business, declined. And if you were FlexFlix, you would be in an uncomfortable position at this point. There was no bug in their algorithm. In the early days, before users had figured out how to game the system, it was working extremely well. And the bug is somehow in how people use the algorithm. And now that they've found ways to cheat it, there's no way to fix it through better queuing and scheduling design. If you were the CEO of FlexFlix, the best you could hope for would be to hire a fresh PhD in algorithmic mechanism design, get that person to talk to your queuing and scheduling algorithm designer about the open research question of how to combine incentives with optimal queuing and scheduling, and hope that there is, a new theoretical discovery that says that you can design a payment scheme that incentivizes the right behavior. So, wouldn't it be nicer if there was a general black box reduction such that instead of hiring a new researcher to design your incentive system, you could take any algorithm, even with bad incentive properties, and do something to it to make it into an algorithm combined with a payment scheme that performs almost as well, or perhaps exactly as well, as the algorithm before running the reduction. Are you the one who asked me that question in New York also, or was it Jennifer?
It wasn't me.
I think it was me.
What was the question?
I said, what's wrong with companies hiring research? Well, what I said was
The answer to that
he's
question.
now creating an incentive for companies not to hire researchers, is what I said. But yeah.
I think it's great for companies to hire researchers, but I also believe in the American small business. And the fact is that most small business owners who are just trying to make ends meet don't have the budget to hire a researcher on algorithm mechanism design. Did you say you have a real question? Thank God. Okay. That is the miracle of Hanukkah.
You take any algorithm and you want to allow, you add payment system to it to make it incentive compatible. Is that kind of
Oh, no. Is it a porn site or something? Oh, but you didn't spell it the same way as on my slide.
no flicks and no practice?
Well, I'll try that too.
Okay. Okay, yeah, what's your question?
So what your goal is to take any algorithm that doesn't have like payment system in it, and you're going to add some payment system to make it incentive.
That is what I'm going to do.
Okay.
Yep. Okay, so our guiding question, can any algorithm be modified to restore proper incentives without overly hurting its welfare properties? One quibble you might have with our guiding question is it's possible to abuse the definition of modified. So for example, here's an uninteresting answer to my guiding question. One way to modify an algorithm and restore proper incentives is to ignore the algorithm and run the VCG mechanism, which has perfect incentives, is dominant strategy incentive compatible, and it always outputs the optimal allocation, the one that maximizes social welfare. The reason that we don't do this is that there are often constraints that prevent you from running the VCG mechanism. There are computational constraints, informational constraints, the complexity for users of expressing their preferences might be too high. Okay, so the guiding question in the form we should have asked it is whether we can modify any algorithm to restore proper incentives, do it in a computationally efficient way, and approximately preserve the performance of the algorithm. This is a question that, in one form or another, many people in algorithmic mechanism design have been thinking about for the last 10 years. And a cartoon version of the answer looks like this. So overlooking a lot of the details, for dominant strategy incentive compatible mechanisms, there is a growing body of evidence that the answer to this question is no. There are problems that are computationally easy to approximate when incentives are ignored and become computationally hard to approximate when you take incentives into account. A more recent line of research that was initiated just this year by Jason Hartline and Brendan Lucier revisits this question from the perspective of Bayesian incentive compatibility, and there the picture looks quite different. And in the second half of this talk, I hope to present a construction that achieves these desiderata for problems that are sufficiently low dimensional, where I'll have to defer the definition of dimensionality. For now, I will say that this paper was the first to give an affirmative answer. They did it for single-dimensional mechanism design problems. And so for those of you who know the Hartline-Lussier paper, what I will be talking about in the second half of this talk is a bounded dimensional generalization of their single-dimensional reduction. And an independent discovery of a closely related result was made by these two students in the same year.
I don't expect a long answer, but we just had a talk by Shad and about a result with Tim Rothgarden. You know,
Yes. Is this
into this picture somewhere? Really?
Yes. If I had written PTAS here instead of arbitrary algorithm, that was the question that Shadden and Tim were looking at.
And the no there, that's for like deterministic mechanisms, right?
The no here is currently for deterministic mechanisms, but I think if you took a straw poll of this set of people and asked them what they believe the answer will eventually be for randomized, you would still get a no.
Which one? The top one or the bottom one?
Let me move on to my next slide. Wait, is there? Oh, I see. The top ones are all Nissan and friends, and the bottom ones are all Papadimitriou and friends. No, Shapira sort of straddles both worlds. Was it? Were you seriously making a distinction between the people in the first line and the people in the second?
Between the people who have proved that the dominant structure doesn't work and those who have proved the Bayesian works.
Oh, these bottom ones. Okay. I am one of these bottom ones, and I would lend my support to the theory that the answer is no for randomized dominant strategy mechanisms. And Brendan is a postdoc here, so you can actually corral him and force him to give an answer on that question.
No.
Brendan is not a postdoc here?
No. He wasn't.
Ah, my mistake.
We can't corral him anymore.
Yes. Thank you for correcting me on that. Okay, this slide reviews the basics of mechanism design. I suspect that most members of this audience have been to a talk on mechanism design, and so I will go through it fast and mostly just use it to demonstrate what my notation is. So my mechanisms are functions mapping abstract profiles of elements of some abstract set that I call bids into another abstract set that I call outcomes. A player is represented by a valuation function that takes their bid and an outcome and outputs a number, which is their value for receiving that outcome, assuming that their bid x reflects their true type. And good. So in mechanism design, an algorithm computes a mapping from bids or tuples of bids to outcomes, as well as a payment function that assigns a payment to each agent based on the tuple of bids. The mechanism designer's objective is to maximize the combined value of all the participants, whereas each player's objective is to maximize their value plus payment or value minus payment, depending on whether the sign convention, whether you represent payments as being from the center to the player or vice versa. Capital Y is a set of outcomes, and when I write f colon x arrow y, it means that f is a function from the set x to the set y, whose input is a bid and whose output is an individual outcome. Single outcome from y. Okay, good. Truthfulness means that every player maximizes their utility by bidding their true type, and we can distinguish dominant strategy. I'll use truthfulness and incentive compatibility synonymously. We can distinguish dominant strategy, incentive compatibility from Bayesian. In the dominant strategy setting, we say that for all tuples of the opponent's bids, you maximize utility by bidding truthfully. And in the Bayesian setting, we assume a prior distribution over the player's bids is given. And the definition says that you maximize your expected utility by bidding truthfully. A final point that I want to make is that when I talk about the Bayesian setting in this talk, I will always be making the tacit assumption that bidders' types are independent random variables.
And the distribution comes in the reduction, and then like usually the algorithm designer isn't thinking of a distribution, is that right? And then when you...
So when I say that this paper gives affirmative results in the Bayesian setting, what I mean is that if you have an algorithm and you have a sampling oracle for the distribution, then you can construct an incentive-compatible mechanism. In my FlexFlix example, it would be debatable whether the system operator has a prior that they can sample from. They have historical log data, so that is something like a prior, but it doesn't anticipate future releases of movies that haven't come out yet. So, like, you know, yeah. But for our positive results, we need to assume that you just have the distribution as a sampling oracle that you can draw samples from. OK, good. Here's a naive false start that doesn't work. So the nicest thing would be if any algorithm could be transformed into an incentive-compatible mechanism simply by using the same allocation function as given in the original algorithm and just combining it with an appropriate payment scheme. But it's actually easy to see that this doesn't work. It doesn't work if f is fatally flawed. For example, if we're running a single item auction and the original incentive incompatible algorithm is the one that picks the lowest bidder as the winner, there is no payment scheme that you can add to that algorithm to make it incentive compatible. So this example illustrates that f has to be a monotone function. What I mean by monotone, at least in the case of a single item auction, is that if I increase any one player's bid while holding the other ones fixed, it can only increase their probability of winning. The converse statement, fortunately, is also true. So if you have a single item auction, or more generally, a mechanism design problem with n single parameter agents, and you have an allocation function which is jointly monotone in this sense, then you can always find a payment scheme that combines with it to make a incentive compatible mechanism. Yeah, so in this slide, I'm talking about a single item auction, and so bids are actual real numbers. Yeah. And more generally, I could be talking about single parameter mechanism design, and then your bid is a number that specifies your marginal value per unit quantity allocated to you. Actually, so for the next maybe dozen slides, I'm going to stay in the realm of single parameter mechanism design. So for now, but not for the entirety of this talk, think of bids as being actual real numbers, and monotone just means monotone in the conventional sense. OK. The formula for the payments that make a monotone function truthful was first discovered, I think, in the 80s by Meyerson. It was rediscovered and generalized by Archer and Tardosh. And the formula says that you charge an agent their value for the outcome they got, minus this rebate, which is the integral represented by the orange area here. So in other words, the amount they pay is represented by the sort of purple-colored area. And the reason that that's incentive compatible is that if someone tries to increase their bid, then their payment would increase by that much, whereas their utility would only increase by that much. Whereas if they try to lower their bid, their utility would decrease by that much, their payment would decrease by a smaller amount. So neither of those deviations is helpful. OK, so if we have a function which is already monotone, and we just want to... Question?
Is monotonicity important, or is it, can you say something about convexity of the CDF? Or does that not make sense?
Being monotone is equivalent to the integral being convex. So
Okay, so we're saying the same thing.
yes. However, your convexity definition is better in the following sense. For a multivariate, for a function from Rn to Rn, the way I will define monotonicity is being a subgradient of a convex function in n dimensions, whereas the definition based on ordering doesn't easily generalize to higher dimensions. But that's anticipating further forward in the talk. Okay, so what does this say about taking an arbitrary algorithm and transforming it into an efficient mechanism? It says that if we have an algorithm which happens to already be monotone, and it happens to be easy to integrate this function, then it's easy to construct the associated payments. So, so wait a second. Is it easy to integrate f? Well, that depends on how complicated the function f is. It could easily happen, for example, that f is a step function with exponentially many steps. This happens quite a lot, actually, in randomized mechanisms where f could be a randomized algorithm that tosses n coins and makes some allocation decision based on the coin tosses, and then the steps correspond to the allocation probabilities for each of the 2 to the n possible outcomes of the coins. Okay, so there's a trick for getting around this by paying people a random rebate, which is an unbiased estimator of the integral. And we weren't the ones to discover this trick. The first place I know of it appearing is in a soda paper by Archer, Papadimitriou, Tardash, and Talwar. The trick is easy to explain. If you take a uniformly random number between 0 and x and compute x times f of t, that's an unbiased estimator of the integral. And so instead of having to compute the integrals, our mechanism can simply evaluate the function f, charge each player x times f of x, and then give them this random rebate, which is an unbiased estimator of their truthful rebate. And thereby, with one call to determine the allocation and n more calls to determine the prices, we get a randomized truthful-in-expectation mechanism. In one of the earliest papers on algorithmic mechanism design, Nissan and Ronan noticed this blow-up factor of n and asked if it was possible to do better. Or is this factor n overhead just an inherent tax that algorithm designers have to pay for the price of having something incentive compatible? This question has motivated a lot of research, much of it on shortest path auctions, where it goes by the name of the replacement paths problem. And there it turns out that computing this integral is equivalent to figuring out not only the shortest path between 2 nodes, but also for every edge on that path, if I were to delete it, what would the shortest path avoiding that edge be? It's also known that for deterministic mechanisms, there exist problems where the factor n plus 1 overhead cannot be avoided if the measure of complexity is communication complexity rather than running time. That's in a very nice paper of Babaioff et al. Okay. Number of players. Oh, yeah, what's a ballpark estimate of the number n? It's the number of players in the mechanism, and so it's application dependent. In an online movie system, could number in the millions. But you know, as a caveat, I just want to say FlexFlix doesn't exist, and if it did, oh, you weren't here for FlexFlix, so never mind. Yeah. Okay, so the original motivation for asking this question was a computational motivation. N might be large, and we want to save computational resources. Another justification for asking it is that evaluating the function may itself be a non-repeatable experiment. For example, F could be the allocation of clicks to advertisers that results from displaying ads in a sponsored search auction. And now, to compute the payments using that formula, I would have to go back and run a counterfactual experiment that says, if you had bid T instead of X, how many clicks would you have gotten given the alternative allocation of display ads that would have transpired in that case? And there's no way to run that counterfactual because you can't present those ads to the users who have already come and gone. So a very nice paper, again by Babaioff et al., looked at this pay-per-click ad auction setting from the standpoint of deterministic algorithms, and again showed a lower bound that said deterministic learning algorithms that are required to compute incentive-compatible payments inherently have worse regret than algorithms that are not required to be incentive-compatible. So you can think of Babaioff as the Grim Reaper who comes along and proves that deterministic algorithms can't achieve what their incentive-compatible, what their non-incentive-compatible counterparts can achieve. He has redeemed himself, however, by contributing the positive result that I will present next. Okay, so our first idea was that one-point estimator of the integral. Our second idea, instead of always giving people a rebate based on this one-point estimate of the integral, 1 minus epsilon share of the time, I'm going to give them no rebate at all. I'm going to do some allocation, and I'm going to charge them exactly the amount they bid for that allocation. The remaining epsilon of the time, the bidder will reap a huge windfall equal to 1 over epsilon times the rebate that I would have given them in the previous mechanism. Okay? So, to a risk-neutral bidder, this is clearly equivalent to the previous scheme I presented, but it has the beneficial property that the extra computational work I do to evaluate f happens only with probability epsilon. And no matter which branch of this decision I take, oh gosh, there's a bug on my slide such that it's actually not apparent. So this is supposed to say f of t instead of f of x. And the point is that in this random rebate mechanism, you make a random choice at the start, but whichever branch you go down, you only evaluate f once. You either evaluate f on the original bid, or you evaluate it on the random replacement, but not both.
So it's just a 1 minus epsilon inverse times x f of t?
Should both of those be f of t down in the second line?
It should be, yes, this and this should both be f of t.
So then it's just 1 minus 1 over epsilon.
Yes, that's right. It's 1 minus 1 over epsilon times x f of t. Yeah. Okay. So this seems great. We're now computing the correct expected payment for each agent. And we're doing it with only one execution of the allocation function f. The trouble is that in changing our allocation algorithm to this randomized algorithm with 2 branches, we're actually implementing a different allocation rule, not the original f, but something that agrees with f with probability 1 minus epsilon, but does something different with probability epsilon. So we're now giving people the rebate that would have induced appropriate incentives with respect to f, but we're no longer giving them the allocation f. What we would like to do is some kind of fixed point of this process of redefining f and then redefining the payments.
I mean, you could still stick with the allocation. Oh, you didn't compute it.
You didn't compute it. Yeah. Okay. And you can't compute it, for example, in the advertising setting because you can't, nature only gives you one opportunity to run the experiment. So all right, so this brings us to our third idea. To get a fixed point of this process of redefining the payments and redefining the allocation rule, we use recursion. Okay, so we modify the rule for resampling people's bids as follows. With probability 1 minus epsilon, you do nothing. With probability epsilon, you replace their bid with a uniformly random t, but then you feed that t back into the randomized resampling procedure, which possibly replaces it again. And you just run this recursive randomized algorithm until it terminates. That is the replacement bid that you spit out for the bidder. Okay? You do this independently for each bidder to get random samples t1 through tn. You plug them into the original algorithm f, and an outcome y pops out. Here comes the rebate. So the amount the payer X pays is their bid times the outcome that popped out, times 1 if their bid was never resampled, and 1 minus 1 over epsilon if their bid was resampled. So you see I traveled into the future and implemented your suggestion that I rewrite the payment rule this way. Okay. And so having now built recursion into the mechanism, we got around the problem revealed on the last slide because we now have a fixed point of the process of redefining the allocation function. So the theorem is that this mechanism is truthful in expectation. It never charges any agent more than the amount they bid. It outputs the same outcome as the original algorithm with probability 1 minus order n epsilon. So by taking epsilon sufficiently small, you can get probability arbitrarily close to 1 of behaving same as the original algorithm, and it evaluates f only once. Of these 4 claims, the last 3 are sort of superficially evident from the way I've described the algorithm. And the first one amounts to saying that the expectation of this random payment is equal to the payment given by that integral formula from a few slides ago. And I'm not going to present the proof of that point, but I hope that the steps by which I led us to this slide have convinced you that the first bullet is true.
So just opening up this recursive call. So
yeah.
The first time you resample, it's resampling a random index between 0 and x.
Yes.
And then it's between 0 and t.
Yes.
And then so
yes.
It's sort of like this decreasing.
So the thing that you output is a product of independent uniform. It's x times a product of independent uniform 0, 1 random variables, the number of whom is geometrically distributed and independent of each of the factors. It may not be obvious, but actually the product of a geometrically distributed number of independent 0, 1 random variables is actually a very simple distribution. You could, what's that? If you take a uniform number between 0 and 1 and raise it to the power eta, where eta depends on epsilon in an appropriate way, you get the same distribution as doing this recursive thing. That may not be obvious, but it's related to the fact that if you run a Poisson process and then take the kth sample where k is a geometrically distributed random variable, then the location of that sample is an exponential distribution. Okay. So that was the main theorem from this paper by Moshe Babaioff, myself, and Alex Slivkins that appeared in EC this year. The paper also contains an extension to handle negative bids, the integral formula that I showed you, as well as its incentive analysis, was based on assuming that all the bids are greater than or equal to 0. The extension to negative bids is actually not a trivial extension, as you might think, but it sort of requires one extra idea. I talked about the application to learning in ad auctions. Our reduction takes any monotone algorithm and transforms it into something incentive compatible, but actually the existing learning algorithms in the literature didn't have the right monotonicity property. So one thing we had to do was design a multi-arm bandit algorithm whose regret scales as well as the best existing ones in the literature, but has this additional monotonicity property. It turns out that that can be done, and the details are in the paper. Although we didn't put it in the paper, it's also easy to extend this to multidimensional convex type spaces. The algorithm must be monotone in the sense that I defined when answering David's question. And in that case, the payment formula is the same, except now it's a line integral in multidimensional space instead of a single variable integral. And the idea of the algorithm is still the same. Instead of multiplying a scalar by this random number, you multiply the type vector by that random scalar. Everything else goes through. The proof is the same as before. I want to transition now to talking about the second paper. And to do that, I want to go back to our guiding question, which was whether any algorithm can be modified to restore proper incentives in a computationally efficient way with little or no loss in performance. And in the first half of the talk, we've seen that the answer is yes, provided that the function the algorithm was computing was already monotone. And so the question now becomes, if you have an algorithm that, your queuing and scheduling policy of your movie sharing site, it already has, sort of good welfare properties, but bad incentive properties. It's not monotone. What do you do to make it monotone? Okay. And to answer that question, I'm going to have to step into the Bayesian setting, which I have heretofore, in everything I presented so far, it was not necessary to have a prior distribution over the people's bids. Okay. To give an affirmative answer to this question, I will now need to assume that we have a prior distribution over people's bids. The different players are independent random variables under that distribution, and we have Oracle access to sampling from the distribution for each player. And in that setting, there are these three papers that answer the question affirmatively under different sets of hypotheses. Okay. At this point in the talk, I was going to discuss what does monotone even mean in the multivariate setting. I've already done that in answering David's question, but I think it's actually beneficial to go through the way that I was going to answer it without using the word subgradient. So let me do that. If I have a function f and a payment rule p that jointly constitutes a truthful single-player mechanism, that implies that the function f by itself has an interesting maximum matching property, represented as follows. So I can take any k-tuple of possible bids of the player, and I can take the corresponding k outcomes that the mechanism would output, and define a weighted bipartite graph where the edge weight from type I to outcome j is the utility of that player type for that outcome. I can then compute the maximum matching in this weighted bipartite graph. And if f belongs to an incentive-compatible mechanism, it must be the case that the matching that f computes is the maximum weighted matching in this graph. I present this alternative definition of monotonicity by way of showing that it's possible to understand monotonicity in purely combinatorial terms without knowing anything about vector calculus and subgradients. No, it has to be one of the maximum matchings. An important example of non-uniqueness is that a constant function always satisfies this maximum matching property because every matching is a maximum matching. Okay. The next slides presented the proof that this maximum matching property is a necessary condition for truthfulness. In the interest of time, I will skip that proof. I should mention, however, that in the literature, this maximum matching property tends to go by the name cyclic monotonicity, abbreviated CMON. It's originally due to Roche. Okay, so, and this is restating what the property is for every player, for every finite subset of her types, and then either for all tuples of the other player's types or in expectation over the other player's types, depending on whether you're talking about incentive compatibility in the dominant strategy or the Bayesian sense. This matching has to be a maximum matching of the bipartite graph.
We're going to need loss later. Can you describe again, what does it mean to have a prior over a player's bids?
Yes. Bids of player I are an abstract set x sub I. And a prior means that there is a probability distribution on x sub I.
So for every player, you get a new player, and knowing nothing about this player, you have some distribution over their bids for these types.
So you
Yes.
do joint distributions on all n?
So the joint distribution is a product distribution.
I see. Okay.
And yeah, what I mean by saying that the algorithm designer has a prior is for player I who has never entered the system, before they enter the system, I can ask the sampling oracle of player I, give me 100 random samples from the type distribution of player I. And I assume the prior is correct in the sense that when player I eventually shows up and reports their actual bid, it is a random sample from the same distribution that the sampling oracle was giving to me when I queried it. Okay, so how are we going to take an arbitrary function f and make it monotone? The first idea is we're not going to input people's actual bids into the algorithm f. We will instead input surrogate bids. So there will be a sampling process that I denote by sigma. It's a random sampling process whose input is the true bid of player I and whose output is a random replacement also drawn from the bid set of player I and with distribution depending on the true bid. And then when I evaluate the f, which is the function computed by the original non-monotone algorithm, I evaluate it on the profile of surrogate types, not the real ones. I require this, okay, so this resampling process sigma, it is a process that takes a bid and outputs another random sample from the same set whose distribution depends on the first one. So it's a Markov chain whose state space is the bid set of player I, okay? And the first property I require of sigma is that the stationary distribution of that Markov chain should be the type distribution of player I. The second property I require is a monotonicity property. That is that the function mapping a bid to the distribution over surrogates should satisfy cyclic monotonicity. Okay. Cyclic monotonicity was previously defined with respect to a mapping from bids to outcomes. And I'm now talking about a mapping from bids to probability distributions over bids. So I need to explain how the definition expands to cover that case. I define the quasi-value of bid x for surrogate y to be the expected value of x for the outcome they will receive if y serves as their surrogate in stage 2 of the mechanism. And this is actually an important definition, so let me repeat it one more time. So the value of player x for surrogate y is the expected value of x for the random outcome that will come out of stage 2 if the surrogate representing them in that stage is y. Under that definition of value, we require the sampling rule to be CMON. And it may appear that I'm making no progress because I originally had the problem of designing a function that satisfies CMON, and I've now reduced it to designing a sampling rule sigma that satisfies CMON. So if it's so hard to satisfy CMON, why is this progress? The reason is that f itself is a function of n inputs, one from each player. Sigma is a function of a single input. And so it turns out to be easier to achieve cyclic monotonicity with respect to univariate functions than multivariate ones, and that's the trick that we're going to take advantage of. Okay, so at the top of this slide, I've repeated the two properties we want sigma to satisfy. It has the right stationary distribution, and it is monotone. If it satisfies those two properties, then the allocation rule defined by the picture on the left also satisfies cyclic monotonicity. Okay, and here's our proof by picture. The first thing is stationarity implies that the bidder in the upper left corner does not know whether she exists in this world, where there are 3 real bidders and we're running the mechanism that I described, or whether she exists in this fake world where she's actually the only person playing the game and a random sampling robot is just generating the bids of the other players. Okay? The stationarity property of sigma says that the distribution of these two is the same whether they're generated by random sampling robots or by running them through the algorithm. And the
sigma distribution was preserving the marginals, was it?
So sigma has the property that it's a Markov chain. And if I input, its state space is the bids of player I. And if I input a random sample from I's type distribution, the thing that comes out is also a random sample from I's type distribution. A different one, but same distribution. Okay, so stationarity says that the left and right worlds are indistinguishable, and monotonicity says that in the world on the right where there's only one player, the function that we're computing is monotone. Okay, so putting those two together, it says that in the world on the left, it's also cyclically monotone. Now you might be wondering how hard is it to design Markov chain sigma that satisfy stationarity and monotonicity. It is pretty hard, but here are two examples to get the juices flowing. So the first one, what about the identity function? This is the Markov chain that takes a state and deterministically outputs the same state. That satisfies stationarity. If I input a random sample from the type distribution of player I, out comes a random sample from the same distribution. It doesn't generally satisfy monotonicity unless f itself already did. Okay, the second trivial example that's worth thinking about is... Yes. Yes. It's an if and only if. Yep. Okay, the second example. The Markov chain resample is the one that I input a bid of player I, it ignores it, throws it away, and draws a fresh independent random sample from the type distribution of player I. Okay? That has the right stationary distribution. And it's monotone because it's a constant function, and constant functions are monotone. It has rather bad social welfare properties, however, because we're ignoring people's bids and giving them a random outcome. How do I quantify that it has bad social welfare? I craft an example of a particular mechanism design domain in which I could come up with a worst case example where there's some distribution and what's a good example? We're running a single item auction.
How do you know that you're succeeding later?
Oh, how am I going to measure social welfare loss? Good. I'm going to normalize people's valuations so that their value for every outcome is a number between 0 and 1. I'm then going to measure the expected sum of welfares for a randomly sampled tuple of players if you run the original algorithm versus running my mechanism. And I'm going to look at the additive regret between those two parameters and try to make it less than epsilon. Okay. Good. So how do we make that additive regret less than epsilon? This is where the remaining crucial idea comes into the algorithm. So in addition to outputting a random surrogate, we're also going to use random replicas. They are also independent random samples from the type distribution of player I. Okay? And let me walk you through. So this slide describes ultimately a Markov chain whose state space is the bids of player I. Okay? It describes a randomized algorithm for taking a bid and outputting a surrogate bid. The randomized algorithm is somewhat complicated, so instead of writing down the transition probabilities of the Markov chain, I've written down pseudocode for sampling from it. And here's how it goes. Before you observe the bid of player I, you draw 2m IID random samples from its type distribution and put m of them on the left side and m of them on the right side. You call them replicas and surrogates. You then choose a random index k and you replace the kth vertex on the left with the actual type of player I. Notice that the distribution of this 2m tuple is the same as the distribution at the end of step 1, because all I did was I replaced one of my IID samples with another IID sample from the same distribution. You then define edge weights the way that we've been doing all throughout this talk. The weight of replica I for surrogate j is the expected value that I will receive if represented in stage 2 of the mechanism by surrogate j. You compute the maximum weight matching. On the left side, you look up which of the vertices is the real player, and you walk over along the matching to the right side and see which surrogate is there. That's the output of the sampling rule. Okay? And as a sanity check to make this peculiar algorithm look more familiar, think about the case m equals 1. Then I just took IID samples, put them on the left and right sides, replaced the left side with the true agents type so that we have the agents type and an independent draw from the same distribution. The matching is the edge going straight across. And that's just the bullet number 2 at the bottom of the previous slide. The thing that I was calling resample is just, the special case m equals 1 in this algorithm. Okay? And the reason you might expect to get better social welfare for larger m is that if I draw 10,000 replicas instead of just 1, then chances are there's, for each of these replicas, including the actual player, there's a surrogate who has quite similar preferences, and our matching will match them to a surrogate with similar preferences. And so it's much... David, you're frowning and shaking your head.
That seems a lot about the probability distribution.
Yes. I'll get to that question later.
This maximum weight matching is not unique, so you're choosing randomly among the maximum weight matches?
Randomly or according to some arbitrary but predefined tie-breaking rule that doesn't depend on the bid of player I. Either one is fine. Okay, so I claimed that this satisfies stationarity and monotonicity. Let me prove it to you. Stationarity is actually easy. Remember I said that nothing changes about the behavior of the algorithm if we omit step 2, which is the only one where we input the player's actual type. So we get the same output distribution if what we did was just take 2m random samples, put down the maximum weight matching, and pick a random edge and output its right endpoint. Okay. Monotonicity. If we condition on all the randomness in this algorithm and just consider varying the bid of the real player, what the algorithm is doing is picking the matching of replicas to surrogates that maximizes the combined utility of the replicas. So that's a special case of the VCG mechanism where the players are the replicas and the outcomes are the n factorial perfect matchings of replicas to surrogates. And we know that VCG is a truthful mechanism, so this sampling rule satisfies cyclic monotonicity if you condition on all of its random choices. Now averaging over all that randomness, the monotonicity property still holds by linearity of expectation. All right, so I hope I have convinced you that this definition does define a truthful mechanism. The only thing remaining to convince you of is that it gets a good approximation to the optimal welfare if you choose a sufficiently high number of samples. David has alleged that that's difficult to quantify, and so I have to respond to that allegation. Okay, here's how we quantify the welfare loss. The welfare of, agent I is just a random one of these replicas. And so the expected welfare experienced by agent I when we run this mechanism is equal to the expected welfare of a random replica for its edge of the matching. The expected welfare of agent I, in other words, is equal to the average edge weight of this matching. If you compare that with what we would have gotten if we had just run the original algorithm, that's, in my notation, that's denoted by V of Ri, Ri. If I did no resampling at all, that would be the value we got. Okay? And so I can think of types as points of a metric space where the distance between two types is the outcome which they evaluate most differently. A type is a mapping from outcomes to utilities. So I can just think of it as a gigantic vector indexed by outcomes. I can put the L infinity metric on those vectors, and in that way I get an embedding of the type space in a possibly infinite dimensional L infinity space. And what I have shown you is that the welfare loss of my mechanism is bounded above by the expected minimum cost matching when I sample m red points and m blue points, IID, and take the minimum cost matching of the red points to the blue points. Okay? The usefulness of this perspective is that the minimum cost matching between two point sets in a metric space is a well-studied metric. It's called the transportation cost. And, probabilists have done a lot of work in looking at the transportation cost between random subsets of metric spaces, and actually quite a bit is known about that question. Not quite enough to solve our problem, but it wasn't too hard to bootstrap from what was known to the following theorem. If you have a metric space of diameter 1 that is partitioned into k to the delta sets of diameter 1 over k, then the expected transportation cost between two random m-point subsets is bounded by this function, which is little o of m, provided that k is large enough and delta is bounded. Okay? So this capital delta, you should think of it as being a dimensionality parameter of the metric space. And to reassure you that I'm using the word dimensionality in a way similar to what you're accustomed to, if the metric space is a bounded subset of a finite dimensional normed vector space, then this delta is always bounded above by the dimension of that normed vector space. So as long as you're thinking of mechanisms where types are actually represented by vectors in R to the D, and the difference between two types can be represented by some vector space norm in R to the D, then rest assured that this delta corresponds to that D. So it's sort of the number of real parameters needed to specify a type or a bid.
So what was k corresponding to in the mechanism?
Sorry. K is just, this theorem has a universal quantifier over k that was omitted because my font size was too large, so I couldn't fit the for all k. But to get the most powerful bound at the end of the theorem, you should optimize over k. Yeah. And it turns out that the optimum thing to do is to choose k equals 1 over epsilon, and m then becomes epsilon to the minus delta minus 2. So what this is saying is that the number of samples we need to draw in our algorithm is exponential in this dimensionality parameter, but only polynomial in epsilon, the welfare loss. In that sense, our reduction is not ameliorating the computational hardness that comes from high-dimensional optimization. What it's ameliorating is the computational hardness that comes from running mechanisms with a gigantic number of players. We're still exponential in the dimension of the optimization problem, but we're no longer exponential in the number of players. Okay, there. The delta is the number of parameters required to specify one player's type. Yeah. Informally, it's the number of parameters required to represent a type. And formally, what I actually need it to satisfy is this covering property when you represent types as vectors in L infinity. Okay. I'm running low on time, so I'm going to skip my remarks about extensions of this result. So summarizing what we get in the end, under various assumptions about how the distribution over players' types are specified, and various assumptions about how what kind of access we have to the allocation algorithm, we get different bounds on the sample complexity of the algorithm. I guess a key point to be made is that for mechanisms with where players have a discrete set of bids of polynomial size, then the complexity of our algorithm is polynomial. For single parameter mechanism design problems, our complexity is polynomial, and in fact a little bit better dependence on epsilon than what was given in Hartline and Lussier. And it's only in the general case where people have multi-parameter bids that we get either polynomial or exponential scaling, depending on how high dimensional the underlying single player allocation problem is. Okay, so ideal. These have to do with how the distribution over players is specified, and these have to do with how the algorithm. This whole reduction transforms an algorithm F into something with better incentive properties. Okay. The question is, what kind of access do you have to F? In the black box model, all you can do is plug in a set of bids and see what it outputs. In the ideal model, I can plug in one player's bid and ask what's the expected value of the outcome when I combine it with random samples from the others type distributions. Okay. Now, you can always simulate the ideal model in the black box model. You can always simulate the ideal model by doing sample averaging. Right? Give me xi, and I can repeatedly draw random samples for the other players, evaluate f as a black box, take the average of the outcomes that I see. But then there's some epsilon sampling error. And so what you get out of that is not incentive compatibility, but it's epsilon incentive compatibility. It's not that people optimize their utility by telling the truth, but they come epsilon close to optimizing their utility. And actually, we had to sweat blood to, in these two boxes, we were able to restore true incentive compatibility rather than epsilon incentive compatibility by using, by tricky means. But in the general case, we don't know how to do it, and I think it's actually an interesting open question. A slide that I skipped that showed 3 boxes being permuted in shell game fashion and a cloud appearing over them illustrates a probabilistic paradox that explains why this box is difficult to fill in. Okay. Good. So just in conclusion, right. I think for the first decade of research on algorithmic mechanism design, people have harbored a bias of believing that designing truthful mechanisms is much, much harder than designing algorithms free of incentive constraints. And much research in the field has been guided by the belief that this should be true and that future recipients of doctorates in algorithmic mechanism design can count on employment at small American businesses like FlexFlix. And you know, the theme of my talk is that sometimes this perception is actually not matching with theory. In some cases, particularly Bayesian mechanism design settings, it's not much harder to design truthful mechanisms than to just design pure algorithms. And the surprisingly powerful tool underlying these techniques is random resampling of people's bids. We've seen how a monotone function can be transformed into a randomized truthful-in-expectation mechanism that evaluates the original function only once, and how any function at all can be transformed into a randomized Bayesian incentive compatible mechanism that evaluates it only polynomially many times for problems with a bounded number of parameters. Okay, so thank you all for coming and listening today, and I'm happy to take any further questions.
So do you think you can actually combine the 2 bullets and actually get all the way with a single call from a...
No. I don't know any theorem that rules it out. But I have no intuition to make me believe that it should be possible. So basically, if you just have this black box that computes a non-monotone function and you can only evaluate the function once, and you want to transform its output to make it monotone, that it's somehow it's hard to believe that there's enough information in that one function evaluation to accomplish that. So yeah, I guess we haven't looked very much into the question of whether you can. I mean, so the sample complexity question of, okay, so we can evaluate it once. How many times do you need to evaluate it is, I think, actually a really key question. And in particular, because I am someone who likes to, because I'm someone who knows about the transportation cost and also likes to look at things in terms of metric spaces, I have chosen to bound the sample complexity in terms of this sort of artificial delta parameter. But it's quite possible that a person with a different mathematical bias approaching the problem from a different viewpoint would come up with a sample complexity bound that is different and in many cases much better. Not by going through the L infinity metric, but by going through some other property of the distribution and the function that processes that distribution. Yeah.
Dimensions of spaces of the axis is not being sort of a fundamental thing, because you can always take any function of it, take sort of a two-dimensional point R2 and just sort of represent it as point R1 by doing some funny transfer.
Interleaving digits or something. Yep.
And so where is it that breaks down your argument that delta actually becomes a crucial parameter? Is it in that sort of minimum distance?
That's right.
Some regularity condition of the function f
that's exactly what happens. So if you try to play funny tricks to represent two parameters by 1, then the utility of agents for outcomes becomes either a discontinuous function or a continuous but not Lipschitz continuous function. It's sort of wildly varying function. And then okay, so that's why instead of defining delta as the number of real parameters you need to use, I defined it in a way that's sort of independent of how the data is represented and is instead a complexity property of the type vectors and the way they sit in L infinity space. So if you're familiar with the definition of Hausdorff dimension of a topological of a metric space, then my delta is just the Hausdorff dimension of the type space in its natural embedding in L infinity. And somehow that embedding is the same no matter whether you interleave the digits and represent them as a single real number or represent them as a pair of real numbers. It just because it's an intrinsic property of how types evaluate outcomes. All right. Well, thank you again.